So in this video we'll solve the remaining sums of magnetic fields due to electric current. So let's look at the first sum. A circular coil of wire is made up of 100 turns, each of radius 8 centimeter. If a current of 0.4 ampere passes through it, what will be the magnetic field at the center of the coil? So solution. So the number of turns in the coil is given to us as 100 turns and the radius of the coil is 8 centimeter, which can be written as 8 into 10 raised to minus 2 meters, and the current in the coil is given to us as 0.4 ampere. So we know that magnetic field at the center of a coil is given by B equal to mu naught Ni upon 2R. So let's put the value. Mu naught is 4 pi into 10 raised to minus 7 into number of turns is 100 into current is given to us as 0.4 ampere divided by 2 into radius, that is 8 into 10 raised to minus 2 meter, and solving this we get magnetic field as 3.142 into 10 raised to minus 4 Tesla. Let's look at the next one. For a proton accelerator, a cyclotron is used in which a magnetic field of 1.4 Weber per meter square is applied. Find the time period for reversing the electric field between the two Ds. So solution. For a cyclotron accelerator, these are the two Ds, D1 and D2, which is connected with an AC supply. Now what happens is their polarity changes from plus to minus and minus to plus in one time period. We need to calculate the time in order to change this plus to this minus, which implies in one time period, that is in one revolution of proton from this D to this D and again back to this D, the polarity changes twice, that is from plus to minus and then again from minus to plus. We need to calculate the time which will be required to just change the polarity once. So that time will be T by 2. Now the time period of the cyclotron is given to us as 2 pi m upon qb, which implies this time T will be 2 pi m upon qb into 2. So 2 will get cancelled, this T will come out to be pi m upon qb. So let's put all the value. Pi is 3.142 into mass of proton is 1.6 into 10 raised to minus 27 kg divided by charge of proton, that is 1.6 into 10 raised to minus 19 into magnetic field, which is 1.4 Weber per meter square, and solving this we get the time to be 2.342 into 10 raised to minus 8 seconds. Let's look at the next sum. A moving coil galvanometer has been fitted with a rectangular coil having 50 turns and dimensions of 5 cm into 3 cm. The radial magnetic field in which the coil is suspended is of 0.05 Weber per meter square. The torsional constant of a spring is 1.5 into 10 raised to minus 9 Newton meter per degree. Obtain the current required to be passed through the galvanometer so as to produce a deflection of 30 degrees. So solution. First of all, let's write what is given to us. So number of turns is given to us as 50 and the area is given to us as 5 into 3 centimeter square, which is 15, and centimeter square is 10 raised to minus 4 meter square. The radial magnetic field is given to us as B equal to 0.05 Weber per meter square, and the torsional constant, that is C, is given to us as 1.5 into 10 raised to minus 9 Newton meter per degree. We need to obtain the current I, and the deflection is given to us as theta equal to 30 degree. So we know the torque is given by C theta, and this torque is equal to NIAB, which is equal to C theta. From this we get the current equal to C theta upon NAB. So let's put all the value. C is given to us as 1.5 into 10 raised to minus 9 into theta is 30 degree divided by number of turns, that is 50, into area we got 15 into 10 raised to minus 4 into the magnetic field, that is 0.05 Weber per meter square, and solving this we get current to be 1.2 into 10 raised to minus 5 ampere. Let's look at the next sum. A solenoid of length pi meters and 5 centimeter in diameter has winding of 1000 turns and carries a current of 5 ampere. Calculate the magnetic field at its center along the axis. So solution, length of the solenoid is 5 meters and number of turns is given to us as 1000. The current is given to us as 5 ampere. We need to calculate B. So the magnetic field at its center of the solenoid is given by B equal to mu naught n I, where your n is number of turns per unit length. So n will, this can be written as mu naught n I upon L, which is 4 pi into 10 raised to minus 7 into number of turns is 1000 into current is 5 ampere divided by pi. So pi will get cancelled, and solving this we get magnetic field to be 2 into 10 raised to minus 3 Tesla, or you can write Weber per meter square. Let's look at the next one. A toroid of narrow radius of 10 centimeter has 1000 turns of wire. For a magnetic field of 5 into 10 raised to minus 2 Tesla along its axis, how much current is required to be passed through the wire? So solution, the radius is given to us as 10 centimeter, which can be written as 0.1 meter, and number of turns is 1000. The magnetic field is 5 into 10 raised to minus 2 Tesla. We need to calculate the current. So we know for a toroid the magnetic field is given to us as mu naught Ni upon 2 pi r, which implies I will be equal to B into 2 pi r upon mu naught n. So let's put all the values. Magnetic field is 5 into 10 raised to minus 2 into 2 into 3 point, let's keep this pi like that only, and radius is 0.1 meter divided by mu naught, which is 4 pi into 10 raised to minus 7 into number of turns, that is 1000. So this pi will get cancelled, this 2 will get cancelled, and further solving this we will get current to be 25 ampere. So let's look at the next one. In a cyclotron, protons are to be accelerated. Radius of its d is 60 centimeter and its oscillating frequency is 10 megahertz. What will be the kinetic energy of the proton? So solution, radius is given to us as 60 centimeter, which is 0.6 meter, and the frequency of oscillation is 10 megahertz. So 1 megahertz is 10 raised to 6 hertz, which can be written as this frequency. So this frequency can be written as 10 raised to 7 hertz. We need to calculate the kinetic energy. Now we know V is equal to R omega. So omega is written as 2 pi f. So V will be equal to R into 2 pi f. Now if V is R into 2 pi f, V square will be R square into 4 pi square f square. Now the kinetic energy is half mv square. So this can be written as half m. V square can be written as R square into 4 pi square f square. Now let's put all the values, that is half into mass of the proton is given to us as 1.6 into 10 raised to minus 27 kg into radius square, that is 0.6 square into 4 pi is 3.14 square into frequency, that is 10 raised to 7 square. So solving this we get kinetic energy to be 11.87 into 10 raised to minus 13 joules. And if you want to convert this kinetic energy into electron volts, divided by 1.6 into 10 raised to minus 19, which will give you kinetic energy to be 7.419 into 10 raised to 6 electron volts, which can be written as 7.419 mega electron volt. So let's look at the next one. A wire loop of the form shown in this figure carries a current I. Obtain the magnitude and direction of the magnetic field at point P. So solution, the magnetic field at point P is given by B, and this magnetic field is due to two components of current carrying wire. One is the curve path and one is the straight. So the curve path current carrying wire and the magnetic field developed due to this is given to us as BABC, and let's name the magnetic field generated due to the straight path as BA or BCA. Okay, so The magnetic field due to curve path is given to us as mu naught I upon 4 pi r into theta. Now this theta is 270 degree for the curved wire, which implies this will be mu naught I upon 4 pi r, and 270 can be written as 3 pi by 2. Now in order to calculate the magnetic field due to the finite length wire CA, let's consider this point P, which is at a distance small r, and these are the end lengths. So the end lengths A and C are making angle theta, which will be equal. So let's name this theta 1, let's name this theta 2, and the distance is r from A and C. Okay, so if this is 90 degree, this whole angle is 90 degree, this angle will be 45, and for this triangle, if this is 45, this will also be 45, since this is 90 degree and some of the angles are 180 degree. So we get similarly for this triangle, so we get theta 1 is equal to theta 2, which is 45 degree. Now the magnetic field BCA will be given to us as mu naught I upon 4 pi small r, since this is the distance from the wire, into sine of theta 1, that is the angle made by one end and the angle made by other end, sine of theta 2. And from here you can clearly see that small r is equal to r sine theta 1 or theta 2, so I will write this as sine 45. So let's put all this value, we will get mu naught I, since theta 1 and theta 2 are equal, which is equal to 45 degree, I can write this 2 sine 45 divided by 4 pi, and small r is r sine 45, so r sine 45. Sine 45 will get cancelled, and you will have mu naught I upon 4 pi r into 2. So now we can calculate the total magnetic field B as BEBC plus BCA, which is equal to mu naught I upon 4 pi r taken common from here and here. What remains inside is 3 pi by 2 plus 2. So this is the magnetic field at point P due to this whole loop of wire. Let's look at the next one. So two long parallel wires going into the plane of papers are separated by a distance r. Okay, so let's take two long wire going into the paper. So both are carrying current I. So this is also going into the paper carrying current I, separated by a distance. So they are separated by a distance r, and we need to calculate the magnitude of the magnetic field at a point P. So at a point P, which is at equal distance from both the wire and subtended by an angle theta from the plane containing the wire. So this is the distance r from point P to both the wire, and this is angle theta which it is making. So if I draw this line, this will be r by 2 and this will also be r by 2. So from this triangle we can say that cos theta is equal to r by 2 by small r, which implies r will be equal to r upon 2 cos theta. So keeping this equation in mind, further moving, we can say that using the right hand rule, that is, if the current is going in this direction, the magnetic field will be like this, and if the current is going in this direction, the magnetic field will be like this. So here the current is going in this direction, so magnetic field will be in this direction, which will come out to be somewhere here for point P. So let's name this as B1, and the magnetic field due to this will be like this, which will come out to be somewhere here. Let's name this as B2. Since we need to calculate the resultant magnetic field at point P, so the resultant will be somewhere here. So let's resolve the components of B1 and B2. So let's take this as the vertical component. So I can consider this as, if this is theta, this will also be theta, and if this whole thing is 90 degree, so if this is theta, this will be 90 minus theta. If this is 90 minus theta, this is also making the same angle, so this will be also 90 minus theta. So this b1 cos component will be b1 cos 90 minus theta, and this b2 will also be, the cos component of b2 will also be in this direction, so I can say this will be b2 cos 90 minus the sine component of both of them will be in this direction, which are equal and opposite, so they will just cancel out, and the resultant magnetic field B will be due to this b1 cos 90 minus theta and b2 cos 90 minus theta. So b1 cos 90 minus theta can be written as simply b1 sin theta, since cos 90 minus theta is sin theta, and this also b2 sin theta. Since b1 and b2 are the magnetic field due to current I, so the magnitude of b1 and b2 will be also equal. So they can just simply be written as b1 sin theta plus b2 sin theta, where b1 and b2 has same magnitude. So I can just write this b equal to 2b1 sin theta, since b1 and b2 is equal. Now we just have to calculate b1. So b1 is the magnetic field at point P due to infinitely long wire at a distance r. So b1 can be written as mu naught I upon 2 pi r, which is equal to mu naught I upon 2 pi. Now this r is r by 2 cos theta, so r by 2 cos theta will come, this 2 and this 2 will get cancelled, so b1 is mu naught I cos theta upon pi r. So let's put this value up here. So b will be b1, that is mu naught I, let's write this 2 here, so 2 sin theta into this cos theta divided by pi r. So putting this value of b1 here, we can write b is equal to mu naught I 2 sin theta into cos theta upon pi r. Now since 2 sin theta cos theta is sin 2 theta, b is equal to mu naught I sin 2 theta upon pi r, which is the same thing that we had to prove in the given question. So I hope you understood this sum. Let's look at the next sum. So figure shows a cylindrical wire of diameter A carrying a current I. The current density, which is in the direction of the central axis of the wire, varies linearly with radial distance r from the axis according to the relation J equal to J naught r by A. Obtain the magnetic field B inside the wire at a distance r from its center. So solution. So since current is flowing in this direction, we know from right hand thumb rule that if current I flows in this direction, the magnetic field will be in this direction. So if the current is flowing in this direction, the magnetic field will be like this around this loop. So this loop will have a cross section area of 2 pi r. So from Ampere's law, we know that close integral of B dot dl. The dl is the length vector along the magnetic field. If we break this loop into small length sections, equal to mu naught I. I is the total current along this wire. So I is the current that is flowing for this section of the wire of radius r. So since B and dl are in the same direction, cos theta will be cos 0, which is equal to 1. So I can write this as close integral of B dl equal to mu naught I. So if I take B outside, this will be close integral of dl equal to mu naught I. Now the close integral of dl will be nothing but the circumference of this loop. So this will be B into 2 pi r equal to mu naught I, which implies B can be written as mu naught I upon 2 pi. Now knowing this, let's calculate the current I. So till now we got B equal to mu naught I upon T pi r. So the current I can be written as current density into area, J into A. Now this area will be what? Pi r square. So I will be equal to J into pi r. Now if we differentiate this, since the current will increase as the radius keeps on increasing, so if you differentiate this with respect to r, we'll have di upon di equal to J into pi r square, differentiation will be 2r, which implies di will be equal to j pi 2r into dr. Since j is given to us as j naught upon ra, so di will be equal to J naught R A. So R will become R square. So 2 pi R square dr upon A. So in order to calculate the total current, we have to integrate from 0 to R. So the total current I will be equal to 0 to R di, which is equal to 0 to R J naught upon A 2 pi R square dr, which can be written as J naught upon A 2 pi R square dr 0 to R. Now this integration will be equal to J naught into 2 pi R cube upon 3A. So this is the value of the total current. Now let's put this value here. So we'll have B equal to mu naught upon 2 pi R into J naught 2 pi R cube upon 3A. So this R and this R are actually same. So I'll just write this as small r, make this change. So this R will get cancelled, this 2 pi will get cancelled, and you will have B equal to mu naught J naught R square upon 3A. I hope you understood this sum. Let's check out the last sum of this chapter. So this sum is also based on this previous problem. We need to calculate the magnetic field inside the wire at a distance r from its center if the current density J is uniform across the cross section. Now in the previous problem, the current density was varying with r. Here they have given that the current density will be uniform. So we can say that solution I was equal to J into A, which is equal to J into pi r square. Now since J is uniform, so this will be the total current. So we can say that magnetic field B will be mu naught I upon 2 pi r, which can be written as mu naught upon 2 pi, sorry, this is small r, 2 pi r into current, that is J into pi r square. So pi will get cancelled, will give us mu naught J r upon 2. So the magnetic field when the current density is uniform is mu naught J r upon 2. So thank you for watching this video.